It started as a report in the New York Times, where David Sanger reported that one of the issues involved in the negotiation, the United States wants Iran to only have, let's say, 1,500 centrifuges out of a total of more than 18,000 that are installed today. The simple way to interpret that is, okay, you have 1,500 and you just destroy the rest. It's a simple process to destroy centrifuges. And that'll work, except Iran said absolutely not, that we will not destroy centrifuges. And so one of the responses was, well, what if we can, the technical term of art is disable the centrifuges, so it's not easy for you to use the excess number. And it would bypass the need to dismantle and or particularly destroy the centrifuges. And Sanger leaked part of this story. I know in my own discussions that it's a serious proposal, but it's by no means worked out. And so what I'd like to do briefly is just talk about what does it mean to do this, how long does it, in a sense, how much time does it buy you? Because if you dismantle something or remove piping, you can stick the piping back on. Well, how long does that take? And then what's the point of all this? And this is, just to give an idea of piping, this shows, this is a European centrifuge plant. It's much bigger than the Iranian plants, but you can see the piping. It's like a maze of piping, and the centrifuges are down below these cylindrical pieces of metal, and the piping rises out of them, and there's different size piping, and so it's quite a maze of pipe work. Here's an Iranian centrifuge, 2 centrifuge cascades, and above is the piping. Here's a single centrifuge, and each centrifuge is going to have 3 pipes coming off of it. And we'll get into this later. In a sense, it's material coming in, and then there's a product coming out, the slightly enriched material, and then there's also, in a sense, the waste, the slightly less or depleted, they call it, or be less enriched than whatever came in. And so that's part of the pipe work. There's also equipment attached to the pipe work. And here I have a picture where you want to measure the pressure inside the piping. It's under, again, we'll cover this later, but it's under vacuum. You want to know the pressure that the gas is at. In this case, that would be the feed. The blue knob is a valve to shut on, turn on and off the gas flow. And so in the pipe work, there's all this equipment to take measurements, valves to control the flow of gas. And so one of the questions is, if you're going to remove the pipe work, how much do you actually disassemble the pipe work? And all this has to do with the speed of reassembly. This one is in the background is a centrifuge cascade at the pilot plant at Natanz, and you can see these 3 long metal pipes. The 3 little ones come off of those. And so again, those long ones are part of the pipe work, and they're quite long. I mean, it's just, and that would have to be removed and somehow stored. This one, the picture's a little hard to see, but this is a photograph of all the pipe work that was being prepared for the Libyan secret centrifuge plant. Khan was a master at contracting out for this work, so all this was being made in South Africa, and this is a picture of all of it. So, and this would be it was about 6,000 centrifuges. So that's in total, at least the front face of all the pipe work. Here, the little pipes are, you can see, well, I'll explain it. They're bound together. The little pipes are in here, so they're bound together. Once you put them into a cascade, you're going to bend them. So it wouldn't be as compact. if you removed them. But nonetheless, it's not a lot of, while it's a maze of pipework, it doesn't take up a lot of space. I think that's all I have. All right. So if the administration did this, they would like to get that it would take around a year to reassemble all this pipework. Because the idea is they want warning time that's sufficient that they can then respond, not in a non-military way. I mean, they don't want to have 5 years from now have to enforce an agreement through bombing campaigns. So they do want to have the time that they could prepare a political and diplomatic response internationally to try to convince Iran not to do it, not to go through with it. It may be Iran isn't trying to build the bomb at that point, it's just reneging on the deal. They may argue, you promised to release or to lift all the sanctions, and yet you only lifted, 80%, and that 20% matters to us, and so we're backing out of the deal. So even in that case, you want to have time to respond, to try to pressure Iran not to do it. With this method, if you just remove the pipes, you could, again, I won't go into the details, but you could probably reassemble in as little as 2 to 3 months. So in that kind of analysis, it's not much time. So in that sense, it's not the best disablement step. U.S. government officials would argue, well, but they're going to run into trouble. It's quite it's a lot of pipe work to put back in for 15,000 or so centrifuges. They're just not going to do it that quickly. So maybe it'll take them 6 months. But nonetheless, in the scheme of things, if they're just reneging on the deal, where they're going to say, oh, we're just going to make low-enriched uranium. You can even have the IA safeguarded. 6 months isn't actually that long of a period of time, and unlikely to get a response. So in that sense, this kind of disablement strategy doesn't work very well, and so people also think of, well, what else can we do? And one proposal that's come up, but is a little trickier, is to not just remove the pipework, but take out the centrifuge that's inside inside this casing. And other proposals are to start destroying things. And this was done in North Korea. Disablement was used at the Yongbyon plant in the late 2000s. And if, I don't know, did any of you remember there was a cooling tower that was blown up? I mean, most of it was disablement, removing equipment that could be put back in, but they blew up that cooling tower. And what that did, and we'll cover it later, is that it disrupted and destroyed what's called the secondary cooling system of the reactor. And you have to dissipate heat from a reactor, and water's a good way to do it. And so it just destroyed North Korea's ability to run the reactor until they fixed that problem. And it actually had a much more significant impact on the restart of the reactor, where the disablement steps that were done, they overcame them pretty quickly when they reneged on the deal. And so the idea is to throw in a little bit of destruction into the Iranian one. And that piece of equipment, a pressure transducer, is a good one to consider because Iran can't make those. It goes out and buys them illegally. I mean, I'm working on a case, or other people at ISIS, where we're expert witnesses in a trial where the U.S. was able to prosecute some Chinese, or particularly a Chinese national, who was involved in an illegal scheme to buy U.S. pressure transducers. That's actually made up in the United States, up near Boston. And so it was acquired illegally through China, and so Iran has a hard time getting these things, and so you could destroy things that they can't easily replace, and then that would lead to delays in being able to reconstitute. The bulk of what I want to cover today is on try to introduce you to the nuclear explosive materials, and it's a lot of this subject is very boring. This is definitely right at the top of boring subjects, but absolutely necessary to understand this. And hopefully you read the the two chapters that we sent you. And traditionally, the way this is looked at is that the nuclear explosive materials are called the long pole in the tent, where if you're going to build a nuclear weapon, there's a lot of pillars, in a sense, or poles that you have to put together. You mentioned weaponization. But the centerpiece, the long pole in the tent, is getting the nuclear explosive material, particularly if you have to make it. And it's what I'd like to do today is talk about 4 nuclear explosive materials. Although I want to emphasize the main ones remain plutonium and highly enriched uranium. Neptunium and Americium are also nuclear explosive materials that you have to worry about, but are not commonly available. Now, I'm not going to give a lot of rigorous definitions. I want to give more of a qualitative understanding of this. And this picture says it all. What you want is a material where, if you have in this case, a neutron coming in, striking a nuclei, that's protons and neutrons, the red and green. It splits it in half, and after it's split in half, more neutrons come out than came in. So that if you have one neutron, and then you have one neutron coming in, here you have 3 coming out. Each one of those neutrons splits another nuclei, and on and on and on. And so you get this exponential growth in the number of events, things fissioned. And each fission releases a lot of energy. And it happens very quickly. And that's what you want in a nuclear explosion. So a very large, rapid release of energy, much greater than you can get with conventional high explosives. And so you want to have materials that are able to undergo an uncontrolled nuclear chain reaction. And that's what's happening, you see in that picture. Now, we'll talk about reactors later. In a reactor, you would like to control this so that you don't have this exponential growth in the number of fissions. One fission happens, let's say in this case there were 3 neutrons coming out, only 1 neutron fissions a nuclei. The other 2 are either leave the area or absorbed in something. But there you can control it, so it's one fission after another. But for nuclear weapons, you want it to be an controlled chain reaction. And so here's a little bit of more technical language. That there are materials able to sustain chain reactions and thus create large amounts of explosive releases of energy. And the nuclear chain reaction occurs when one nuclear reaction causes an average of 1 or more nuclear reactions, thus leading to self-propagating series of these reactions. And again, we'll provide these slides. In fact, did everyone get the slides from last week? We're having trouble with the video. We can't load it on our website. Mm-hmm. We didn't realize that. It's available, but
we'll find a way.
We'll figure out a way, but we'll. And again, as the long pole in the tent, nuclear explosive materials are expensive, difficult, and often very dangerous to produce. And typically their production requires large capital expenditures and the mastery of a wide range of technologies. And also whether it's plutonium or highly enriched uranium, the way you do that differs very, very dramatically. Poses very different technical challenges. And the fact that it's a challenge is one of the reasons why there hasn't been a lot of proliferation. There's been many more efforts by countries to get the bomb by far than there have been successes. They start and they will face a technical challenge they can't overcome, or it'll take so long that the political leadership will change its mind or not decide to do it, and then leadership can change. So a good example would be Sweden or Canada. Canada was a member of the Manhattan Project, put together a plutonium production reactor after the war, produced separated plutonium, and then just decided not to build weapons and decided to not pursue that path by the late 40s, early 50s. Sweden had a nuclear weapons program, and it was taking a long time to reach a point where they could make the materials, and they changed their mind. The leadership changed. Same with Switzerland, also had a nuclear weapons program. Nonetheless, too many succeed. And it's, I forget, well, what is it, 9 countries now have nuclear weapons. And only as one has given them up, South Africa. If you're going to stop this, if you want to slow proliferation, then it makes a lot of sense to try to interfere in countries' abilities to get these facilities. And if you're worried about terrorism, then it makes a lot of sense to keep them from getting already produced quantities of plutonium or highly enriched uranium. And so there's also going to be a diplomatic aspect to this, and that would be the joint plan of action, and nuclear security summits would be the political activities you may undertake to slow this down. And also export controls are very important in this. Now, I think I've mentioned already the main types, and what I'd like to do is just go through each of these. The highly enriched uranium, plutonium, Neptunium-237, Americium, and I won't go through uranium-233. That's another one. Now, the basic information on highly enriched uranium, again, I need to define an isotope, where I'll do it in the context of uranium, where they have uranium isotopes have nearly identical chemical and physical properties, but different nuclear properties. And so they all have the same number of protons, 92, but they have differing numbers of neutrons. And that's why they say uranium-235, uranium-238. Uranium-238 is the abundant one in the Earth's crust. And uranium-235 is what we call fissile. And again, this is a technical definition. I mean, you often hear, the Fissile Material Control Treaty, but the term itself, fissile, means that it fissions when it's struck by relatively low energy, and they're called thermal neutrons. And uranium-235 will fission more readily when it's struck by a slowed down neutron than when it's struck by a fast one. When it comes off after a fission event, it's going to come out at a very high speed. And so but if it's around water, again, I'm throwing all these terms at you, but a moderator, it'll slow down through a series of collisions. It'll slow down essentially the speed. Now, uranium-238 is not fissile. So thermal neutrons will not fission U-238. But when they're fast neutrons, such as when it comes right off of a fission event, both uranium-235 and uranium-238 will fission. And all these things have applications in nuclear weapons. These are again, all you can do is memorize these. Just the way we describe different types of uranium. And natural uranium, what you find in the ground, in seawater, it contains about 0.71% uranium-235. So that's what occurs naturally now. It hasn't always been this way. Long ago, there was more of a fraction of uranium-235 in the natural uranium, but the uranium-235 decays faster than uranium-238. But right now, it's about 0.71%. And so if you're going to dig it out of the ground, mine it, that's about what you'll find. Depleted uranium, and this comes up in enrichment, is anything that contains less than 0.71% uranium-235. So it's been, the fraction of U-235 has been decreased. Low enriched uranium contains more than 0.71% uranium-235, but less than 20% uranium-235. And then highly enriched uranium, which by definition you could use to make a nuclear explosive, contains greater than or equal to 20% uranium-235. And so if you're going to create standards of physical protection, you're going to protect the highly enriched uranium more than the low enriched uranium. And so in the real world, what you see, for example, is if you have a research reactor and you want to use as much enriched uranium or get as high a fraction of uranium as possible without triggering special physical security requirements, you'll use 19.75% enriched uranium. And so if you follow the Iran debate, it's always called near 20%, 19.75% that's used in the Iranian research reactor, and the whole point is to avoid it being called highly enriched uranium, which it would be if it was 20%. And yet you want the higher enrichment. Weapon-grade uranium is a subcategory of highly enriched uranium. So it's more than 90%, or greater than or equal to 90% uranium-235.
Could you make a nuclear explosive device with just uranium-238? Because it still does fission.
Not as self-sustaining, but if you put it in a thermonuclear weapon, again, you'll be producing fast neutrons because it'll be fission events, and then that can fission, and that was one of the innovations of the 50s, because you can then get a tremendous boost in the yield by putting in a lot of uranium-238 around the device.
Use it as an explosive as a secondary, basically.
Yes.
Okay.
Yeah. Any questions on this? And again, you just have to memorize these, and I'll throw these terms around quite often in our various discussions. So please be very familiar with them. And LEU is HEU. These are all commonly used terms. Now some general principles. A self-sustaining chain reaction in a nuclear weapon cannot occur in depleted or natural uranium. It's theoretically possible to achieve a self-sustaining chain reaction in LEU enriched to about 10%. But in practical terms, again, a group of scientists, nuclear weapons experts, sat down in this country and decided what's practical. And I knew one of the people involved in that effort, a guy named Carson Mark, and they decided that, 10% is possible, 12% is possible, but from a practical point of view, you're going to need 20%. And that's going to be a big device. Not as big as a house, but it'll involve hundreds of kilograms of HEU that you're going to have to somehow compress in an implosion system or use in a gun-type device. Yes?
I have a question from Henry asking, where does MEU fall, presumably in the uranium?
Well, I didn't define it. MEU is typically around 45% enriched uranium. That's 45% in that area.
What was that?
Oh, what is medium enriched uranium? Oh. Yeah. I don't use it very often, but but again, this 20% is established as a rule based on, in a sense, the ability to form a self-sustaining chain reaction combined with the practicality of actually building a nuclear explosive device. And again, this is not going to be deliverable. It's just way too big to deliver, but you could construct it. And then again, as I mentioned earlier, this triggers additional requirements on physical protection, greater care with the material. So it's a meaningful limit. But if you're a nuclear weapons designer, you're really going to be you're going to want to have much higher enrichment levels. The first South African device were about 80% enriched. Hiroshima was about 85% enriched. But you'd like even higher than that, and typically you want weapon-grade uranium, 90% enriched or more. And the reason is you need less of it. If it's more enriched, you're going to need less of a total mass. that makes your life to build a weapon a lot easier. But it also, the last bullet is that the low enriched uranium, typically the material used in conventional nuclear power, has no military value, typically as a material. But as we've learned in proliferation, and that it has tremendous value to a proliferator because it's most of the way in terms of effort to having weapon-grade uranium. So if you have a stock of low-enriched uranium and you're enriching it further, you're actually about 70% of the way to weapon-grade uranium. So it's required a kind of a rethinking of low-enriched uranium combined with an enrichment plant. And a lot of the debate on Iran is on how do you reduce their stocks of low-enriched uranium. The next one is plutonium. And plutonium, as a general statement, does not occur in nature. It must be manufactured. And plutonium-239 is the most desirable isotope for nuclear weapons. And the way you produce it is you irradiate with neutrons uranium-238. So it's absorbed in the U-238, it goes through a decay process, and then you end up with plutonium-239. And so the easiest way to do that, although by no means the only way, is using a nuclear reactor. And so if you look at the Manhattan Project, the effort was made to create reactors where you could make the plutonium. Its half-life is much shorter than uranium-235 or 238. So it's much more radioactive, requires much greater care if you're going to handle it. And again, I don't know what you've seen, but have you ever heard of glove boxes? I mean, if you're handling weapon-grade uranium or highly enriched uranium, you're going to take care. You don't want to breathe it in. But if you're handling plutonium, you're going to make sure the plutonium is contained in a sealed environment. And so a glove box handling, again, this would be plutonium metal or powder, you would have a sealed environment, and then you'd have these kind of rubberized gloves, and the operator would stick their hands in the rubberized gloves and then manipulate the plutonium and move it on to other places. But they want to make sure they don't inhale it or get it on their skin, because it is so much more radioactive than uranium. And that creates problems and expenses if you're going to go that route. The obvious advantage is that a lot less is needed in a nuclear weapon, and the IAEA safeguards criteria, which I don't know if we'll have time to talk about it very much, but Sweden did a study. No one knew it had a nuclear weapons program at that time, but it volunteered to create a kind of price out a nuclear arsenal as part of its work for nuclear disarmament, actually. And it did studies where it said, look, you have 25 kilograms of weapon-grade uranium, you have 8 kilograms of plutonium. That's enough. Each of that quantity is enough to make sure you can build a bomb.
It's an SQ, right?
And that became what's called, well, an SQ is slightly different. Well, no, this is stated right. 25 kilograms of uranium-235 in weapon-grade uranium. So that would be an SQ. And the same with 8 kilograms of plutonium. Now, you can make it with less, but that amount will be enough with losses, so you could make it. And at the time, people didn't appreciate that Sweden had looked at all this stuff pretty thoroughly as part of a bomb program. But these became the standard values for what you need to make a nuclear weapon. Now, if plutonium-239 is produced in a reactor, it's produced in uranium-238. That would be the fuel in the reactor. Plutonium-239 itself can absorb a neutron, and that can lead to plutonium-240. That can absorb a neutron. And so you get other isotopes, such as plutonium-240, 241, and 242, that complicate this situation. And it turns out that plutonium-240 is particularly challenging. It has a relatively short half-life, which means it produces heat, because again, fission produces energy, which can become heat, and it also produces more neutrons. And that complicates the ability of a nuclear weapon to detonate effectively, and it complicates the storage of the nuclear weapon. So traditionally, bomb makers want to have plutonium that minimizes the amount of plutonium-230, 240, but at the same time, you're running a reactor, and you want the reactor to produce a significant amount of plutonium-239. So you want the, in a sense, the fuel to stay in longer, but that means that the 240 is going to build up, 241, and so there's an optimization that has to go on, a decision that has to be made. How much plutonium-240 will you accept? Now, in fact, let me jump ahead one. This led to the development of what are called grades of plutonium. These are the US definitions. Russia uses different ones. I think Russia decided that its grades are classified. Other countries may use other ones. But in the United States, when people talk about weapon-grade plutonium, it contains less than 7% plutonium-240. And so there you have the balancing. Okay, we want to produce more plutonium, leave the fuel in longer, but that means more plutonium-240 is produced. Well, we take it out when the plutonium-240 level reaches 7%. Now, plutonium is produced in fuel. The fuel may have nothing to do with making nuclear weapons. It just stays in the reactor. And there's two other grades. There's fuel grade, which it has plutonium-240 concentrations between 7 and 18%. And then reactor grade plutonium, which is typically the kind of plutonium that is discharged from nuclear power reactors, contains more than 18% plutonium-240. Again, these are just definitions you just have to memorize. We won't use them that much. We'll use weapon-grade plutonium a lot. Now,
question?
Yes.
Oh, just quickly, how do you feel about IAEA's SQ definitions? Do you feel like they're accurate, or I guess
I used to care. I mean, I was involved in debates. They should be lowered back in the 80s, early 90s. But there was once the IAEA started having nuclear weapons experts advise it directly, they'd have them on staff. I think they developed a more sophisticated understanding. So the SQ drives some of the safeguards procedures, but they're looking for much smaller diversions. So they know that smaller quantities can be quite dangerous. So I think the values were left intact, and I agree with that. But the attitudes about diversion and threats became more sophisticated. But clearly, you can make more. Department of Energy in the 90s declassified that you can use 4 kilograms of plutonium to make a nuclear weapon, and North Korea, believe it or not, declared in 2008 or so in its declaration under the Six-Party Talks that it used 2 kilograms of plutonium in its 2006 nuclear explosive device. I mean, there's a lot of skepticism about that. That's a small quantity, and it may be some elaborate scheme of North Korea. God knows what. I mean, I once had a debate with a very senior North Korean official. She asked me at a Track 2 event back in it's a long time ago, 2005. How much plutonium does the U.S. use in nuclear weapons? I sort of just flippantly said, I don't know. It's classified, 2 kilograms. And she said, we can do better. And so I always in the back of my mind, she was very senior and very involved in all this. And she would be involved in the declaration. I always thought in the back of my mind as she grabbed onto the 2 because of that discussion. So and that's the basis of it. It may have no basis in reality. They may have used much more. But it's through people, for sure. I mean, it's a very small amount. Now, one of the surprises in all this was, if you're thinking about this, plutonium-239 is the desirable one. Well, if you're making reactor-grade plutonium, you're running a nuclear power program, you want to separate the plutonium, you would naively conclude that, in a sense, dirty plutonium can't be used to make a nuclear weapon. It just won't work. there's so much plutonium-240 that it'll keep the nuclear weapon from working. And one of the unfortunate surprises was that no, that's not true. That even heavily, or even plutonium with large fractions of plutonium-240 can be used to make a nuclear explosive.
Yeah, just the chances of fizzling are greater.
That's right.
That
But
doesn't mean that it won't work.
yeah, and I should have put in a graph. There's a graph on the Nagasaki yield that's been declassified, and it was just like when they designed it, they didn't know the yield they'd get. So let's say it's a Trinity device.
Yeah.
It could have gone from 1 if it had pre-detonated, and it went critical, right when went critical at the beginning, or it's compressed a great deal, and then the chain reaction starts. So I guess I should say it is if the chain reaction started right when it went critical, it's compressing. Some point it goes critical. If the chain reaction started, my memory is you get 1 kiloton. If it continues to compress before the chain reaction starts, you can get up to 20 kilotons. Now the way they designed it, it got closer to 20 kilotons. So it worked very well. It turns out, if you think about it, plutonium-240 is going to flood the nuclear core with neutrons. So as soon as that device goes critical, the chain reaction will start. And so that bottom value is the yield you'd get if you used reactor-grade plutonium with a device designed like the Nagasaki device or the Trinity device. I mean, is this clear?
Kind of, yeah.
There was also in the 50s unlimited amount of money to study nuclear weapons, and they were able to test all the time. And so the theoretical division at Los Alamos, run by Carson Mark, who I mentioned earlier, thought, well, what happens to critical mass if you increase the amount of plutonium-240? So they started to study the effects of 240 on critical mass. They conducted an underground nuclear explosive in the early 60s with much higher fraction of plutonium-240, and it worked. And so that was very heavily classified for a long time. But they not only studied it, but they proved through an explosive that it would work. Now, it wasn't 20%, it wasn't reactor grade, but it was well into the fuel grade.
So for estimating yield now, I mean, do most people just kind of use measurements from the CTBT system, or how do you?
Well, you'd have a theory. You'd have a theoretical. And if you're going to build a nuclear weapon, there's going to be a lot of devotion to the theoretical aspect of it. I mean, a terrorist group isn't going to do that, obviously, but they'll do some. But if you're going to build it as a nation, you're going to spend a lot of time, and so you'll have, in a sense, a yield curve, but you won't know how well it'll work.
I mean, after the fact. So when North Korea tested, most recently, people were saying, "Oh, is this yield? Is that yield?"
Well, think of their first one. They thought they would get 4 kilotons,
Yeah.
and they got less than a kiloton. So something didn't work. It may have pre-detonated. Something may have just not worked right.
But I guess what I'm asking is, how do they get to the less than 1 kilogram?
Well, it could pre-detonate, and it's a different design than Trinity, so it's going to have a different yield curve.
And so
It may have just, something may have failed, and the neutron initiator went off too soon. And
shielding, I can't remember. Does shielding relate?
no,
Okay.
there won't be shielding that would affect this. And we can cover more of this. I mean, we can go into this. Again, it just depends on what you want to learn. There'll be some flexibility. But there is a lot to cover in this course. And we can give you additional readings. That the declassified literature is pretty broad on this. There's also plutonium-240 creates heat, and this is a serious problem. I mean, if you hold plutonium, it'll be warm to the touch. Well, with 240 in it, it's going to get really warm to the touch. High explosives around something is going to act like a big blanket, and the heat's just going to build up. It's an insulator, so you have to have a way to dissipate the heat. And so on balance, when you combine the fact you're not going to get a very good yield, I mean, you can use very advanced techniques, and maybe we'll cover them, boosting, tritium boosting. You can use advanced techniques. In fact, it's similar to what you asked. It's like you're producing the neutrons through another means, and that's fissioning all the plutonium, 240 included. But on balance, you don't want to use this in a nuclear weapons program. I mean, it's just not desirable. And also, Carson Mark found is that you increase the 240 amount, the critical mass changes, but what does that mean? If you want the same yield in your design, you have to stick more in. So if you're manufacturing a nuclear weapon and you're making lots of them, the last thing you want is a case where, well, if it's this amount of 240, it has to be this big. If it's that amount of 240, it has to be this big. You can't. Every weapon would have to be built individually. So for standardization reasons, you also want a fixed plutonium 240 value, and then all the weapons can be built the same. So again, you don't find any country that's gone the route of using plutonium with high 240 content. Now, doesn't mean it doesn't have to be protected, because it's not a bad material for terrorists. Because I mentioned this last time, you don't need a neutron initiator. If all you're trying to do is work up an implosion system that is going to get you a critical mass, that the implosion system works, the 240 will create the neutrons that will initiate the chain reaction, and you'll get up to a kiloton.
Well, and the thing is, for terrorist purposes, even a fizzle to get a point across.
Yeah, no, it could be 100 tons would really be devastating.
They don't necessarily need a chain reaction for.
Yeah, well, a dirty bomb. That's right. It could just be dispersing plutonium. But even, and this I will cover. We throw around these terms. I throw them around 20 kilotons, 100 tons. I mean, those are big explosions. Yeah. Typically in big bomb dropped in Iraq is 500 pounds, 250 kilograms. So multiply that up by 1,000. So these are big events. One thing that there is now that there wasn't when I was young, there's all kinds of programs. I think Federation of American Scientists has one where I think you can even use it, where you put in whatever you want, 5 kilotons, 100 kilotons, and then you see the blast effects on New York City. So with computers, you can understand this much better. Here's from the CIPRI book. And again, it gives the half-lives, it gives the isotope for plutonium, the half-lives, and then some properties. Typically, what's on the far right is the isotopic concentrations for various types of plutonium. So they run vertically. And there's also an isotope plutonium-230 that starts to show up in significant amounts as you irradiate the plutonium more.
Can you explain what a Magnos reactor is?
I will later.
Okay.
Yeah, it's just a type of, it uses a graphite as a moderator and gas, carbon dioxide to cool it.
Okay. The other question I was going to ask is, fast breeder reactors, how much more plutonium, like, does it look, if it were like another column?
Well, the fast breeders, again, these reactors, it's called a pressurized water reactor. Magnox CANDU is a Canadian design. They're going to work by, I mentioned thermal neutrons.
Yeah.
They're going to take the fast neutrons that come off of fission and slow them down, and then those will fission the uranium-235. A fast reactor runs off of fast neutrons, and so it uses.
It's more than it consumes.
Well, in theory, that's right. But that's a design phenomena of the core out of plutonium or weapon-grade uranium is going to fission through fast neutrons. Then you're going to have excess neutrons, and then there's going to be a blanket of material around the core of depleted uranium, and so the excess neutrons that escape the core would then irradiate uranium-238 in the core and make more plutonium. But it works very slowly, and And there's not a single fast reactor using plutonium in the world today of any size. They build them and they just had safety problems. But we'll cover some of that. Now, the last two things I want to cover is Neptunium-237. Again, that's in the chapter. I'm going to have to skip over it now. But it's a very useful nuclear explosive material. There's a lot of it in the world, but it's in irradiated fuel or in high-level waste. It's been used by weapon states to make plutonium-238, which can be used as a power supply, like if you want to do space travel. So you radiate Neptunium-237, you can make plutonium-238, which can then be used as a power supply because through its radioactive decay. So the United States and Russia actually made it and produced it, separated it for that use. One of those countries tested it. I can't remember. We actually, it's in the chapter. Did anyone read it? Did the U.S. test a device with neptunium? I can't remember. And it's because it's long half-life, it doesn't have any heat problems. And as I mentioned before, it can be used in both a gun type and an implosion. It's not safeguarded. I mean, you think all these explosive materials are safeguarded by the IA. This one is not. It's recognized as a problem by the IA, but non-nuclear weapon states, countries like Japan, they don't have much separated neptunium. And so the IA will safeguard it formally if the amount of separated Neptunium-237 exceeds a certain level. But so far that hasn't happened.
France did?
I'm sorry, but France is a nuclear weapon state.
Oh, sorry.
So it doesn't count. Yeah, and so did U.S. and Russia. But it was a hole. I mean, part of the game in non-proliferation is what are the holes? Well, if you're a proliferant state and you want to think of a hole, neptunium was one of them. Let's say you had a reprocessing program, which Japan did, Germany did. You're separating the plutonium out of the irradiated fuel. A lot of fission products and things like neptunium go into the high-level waste and are put into tanks. None of that is safeguarded. So the loophole was a country could take its high-level waste and pull out the neptunium. And so the additional protocol, if you know what that is, actually has a clause to catch that loophole. Traditional safeguards agreement doesn't.
Most of those see the additional protocol usually.
Most have, yes. Certainly Japan has, and the countries with reprocessing waste. The last material is Americium. Well, is that the same? Oh, it's just more properties. The last one is Americium. This one actually does generate controversy. Countries will argue Americium cannot be used to make nuclear weapons. It's just too short half-life, it's too hot, it's just too radioactive. The U.S. believes it can be, and declassified information, which is in that chapter on Americium Neptunium, to say that it can be. And Americium originates from the decay of plutonium-241, which again is produced in the reactors. So it's in the high-level waste, it's in the spent fuel.